Hi all, today we are introducing chemical reactions and also balancing equations. For those of you that are absent, I wanted to highlight the fact that we are starting our chemical reactions unit. We got a calendar today, we started filling in the summary sheet, and we're going to be doing a lot of labs in this unit, and every single time we're doing a lab, we are trying to kind of demonstrate these 5 skills that are highlighted, that are the kind of underlying constant refrain of our labs. And so today we're going to be working on these first 2 things. We're going to talk a little bit about how to take a reaction from words to chemical equations. We're also going to talk about how to balance a chemical equation and how that relates to the conservation of mass or matter. So the really amazing thing about chemical reactions, as we know from last semester, is that in a chemical reaction we have the same atoms and the same number of those atoms at the beginning and at the end. All we changed is how they're connected to each other. So that is what a chemical reaction is. And when we're going into this, important note that I wanted to make sure that we talk about and write down is that anytime you are going to 7 specific things, they are going to be by themselves, but they're not really by themselves because they bind to themselves. So generally when we have atoms, right, in a chemical reaction, they're connected to something at the beginning, they're connected to something at the end, and we just changed how they're connected to each other. One important exception to that is that there are these 7 atoms that are incredibly electronegative and very reactive, and when you put them into, if there's nothing else for them to bind to, they will bind to themselves. And so we've got hydrogen as one of them, nitrogen, fluorine, oxygen, bromine, chlorine, and iodine. So if at any point you're writing an equation where you are making something like hydrogen gas or oxygen gas or fluorine, chlorine, bromine, iodine, nitrogen gas, all of those gases are not one atom floating around on their own. They are 2 of that atom together, and we can see that in their formula, N2, I2, Cl2, etc. What I wanted to point out is if we look at the periodic table, again, we know hydrogen's fairly electronegative as a nonmetal. And also, hey, fluorine is the most electronegative, followed by oxygen, and then nitrogen, chlorine, bromine, and iodine. So that repeating pattern of this corner of the periodic table being very electronegative and kind of something to keep an eye on shows up again in this unit. And I just wanted to make sure that that didn't get lost in the rest of the unit or the rest of today's lecture starting out. So anytime you see hydrogen gas, chlorine gas, nitrogen gas, etc., that's going to be a diatomic molecule, which means it's written as H2O2, etc. So taking a step kind of back and a little bit broader, just looking at what is a chemical equation. Well, a chemical equation is always written like this. You have what are called your reactants. Those are on the left side. You put an arrow to show that a reaction is occurring, and a one-way arrow is saying it's a one-way direction, one-way reaction, and then you're making products, all right? Generally, you're going to have more than one, right? And generally, you're going to have more than one on either side. But sometimes we'll have one and it breaks into pieces, or we'll have 2 and they combine to make one thing. But in general, when we talk about a chemical equation, we're going to say, oh, you have this many reactants or reagents, and they produced your product. There are 5 types of chemical reactions in general, and these 5 types are pretty important. We've got synthesis. Okay, synthesis is when we have two molecules or 2 atoms coming together and making one. So you can see we got this hypothetical A plus B is producing AB. Decomposition is the opposite. These 2 are opposites of each other. In this case, we have 1 reactant, and that 1 reactant is breaking into 2 products. All right, a single replacement reaction. In a single replacement reaction, we have 2 different reactants, and we have, two different products. The thing that changes in a single replacement reaction is that C moves in and kind of replaces B. So we can see that we have a molecule of AB, and this C atom is all by itself. And then at the end, we have AC, and now B is by itself. A double replacement reaction, well, that's very similar to a single replacement reaction. We can see that our cation-anion pairs switch. So these are ionic, a mixture of two ionic things that are going together. And we can see that A was previously with X as a reactant, and after A is now with Y. We've got B with Y, and at the end we've got B with X. In combustion, we have some sort of hydrocarbon, so that's C's and H's, and O's possibly, being added to oxygen. There's one of the Q's. And then a very important thing, your product for a combustion in our class as a combustion of a hydrocarbon is always going to be producing carbon dioxide, water, and energy. You can have a combustion that's kind of more like a synthesis for metals, but to simplify our pattern recognition and still be accurate, we're working with hydrocarbons being intensely oxidized, so being combusted, just producing carbon dioxide, water, and energy as an exothermic reaction. It came back. Onward. So, a couple examples here. We've got sodium, solid sodium metal, plus chlorine gas, producing an ACl, table salt. Here we've got hydrogen gas, oxygen gas, producing water. So one of the important things about equations is a lot of times they'll tell you the state, and that's a clue about what's going on. And so these states are important. If you have an S, that means it's in a solid state, your typical kind of solid-looking material. Gas, it's a gaseous state. We may not be able to see it. We may see bubbles a lot of times. L, liquid. It's just saying that you've got a liquid form of that particular molecule. And then AQ. So AQ, an aqueous state is important, comes up a lot, especially in those replacement reactions. An aqueous thing is saying this is dissolved in water. So we have this ionic compound that dissolved and dissociated in water. And now when we mix it with something else, those ions are free to do replacement reactions with each other of some sort. So an aqueous solution is saying that you have a solid that's dissolved in water. So we will see those show up. So we kind of know what a chemical reaction looks like, or a chemical equation looks like now. It looks a lot like the formulas you've seen throughout the years, right? You all have seen, O2, you've seen Cl2. If we go back, you've seen some of these kind of symbols before and the formulas before. What I want to talk about is there's some rules that underline whether a chemical reaction will occur. And one of those rules is the conservation of matter. So we talked about conservation of energy last semester and how energy in a system can't be destroyed. Just like that, you can't destroy matter. We have to have the same number of atoms and type of atoms on both sides of a chemical equation. So no atoms can disappear in this process. You have the same number of carbon atoms at the beginning as you did at the end. They're just connected in a different way. So that's an underlying rule that's very, very important in predictions and in just understanding chemical reactions in general. So again, we have to have the same number and same type at the beginning and at the end. If I have, a gold at the beginning, one gold atom, I have to have one gold atom at the end. It can't magically become something else. So the conservation of energy is really important. in chemical equations, and what that ends up looking like and how we show that principle is called balancing an equation. So if you look at the equations from before, if I click back real quick here, you can see in this first example, I kind of split and I look at the reactants for a moment. I have 1 sodium and I have 2 chlorines on the left side, on the reactant side of this equation. But then over here, I've got 1 sodium and 1 chlorine. So this is not a balanced equation. This is not reflecting the conservation of mass, the principle of the conservation of mass. If we tried to go into the lab and do this, we'd probably be frustrated because we wouldn't get the maximum return for our efforts and our time in the lab using an unbalanced equation. So again, too, let's look at this one. I've got 2 hydrogens on the left. I've got 2 oxygens on the left. I've got 2 hydrogens on the right. Yay! But I've only got 1 oxygen on the right. So my product is short an oxygen. Not fair, not right. We have to have even numbers on both sides. So if we look at it, we've got a balanced equation here. So I went ahead and put a 2 in front of Na and a 2 in front of NaCl. And now if we count, you can see 2, I have 2 sodiums, okay? I've got 2 chlorines. Those chlorines are connected to each other, but I have 2 of them. Now at the end, I have 2 of 1 Na plus 1 Cl. So I have 2 Nas, I have 2 Cls. We're balanced. Great. Here I have 2 times 2 is 4, so 4 hydrogens. I have 2 oxygens in my reactant. Over here, I have 4 hydrogens and I have 2 oxygens in my product. So now that is balanced. Well, you might be like, hey, why can you mess, what's this number mean? Why can we mess with that number? Well, the number that is in front of a molecule, right here, and right here, right, those numbers that I added are called coefficients. And we can add those, all right? We can add a coefficient. So a coefficient is showing how much of a particular molecule you have. For example, I have 2 H2Os. I have 2 water molecules. That is what a coefficient is showing. It's that you have 2 of that molecule. A subscript, which is what you've worked with more before, is showing how many of a specific atom are in the molecule. So if you think of those models from last semester, you know, this was your recipe. This is what tells you how many of each one you need. So you grab 2 hydrogens, you grab 1 oxygen, and you put them together, right? So a subscript shows you how many of a type of atom are in your molecule or connected to each other. And a coefficient tells you how many of that molecule you have. We can change coefficients to balance. We cannot change subscripts to balance. If we look at kind of a little bit of a silly example here, but I think still a helpful one. Okay, if you're making a cheese sandwich, all right, and I have 2 BDs, so I have 2 breads, and I have 1 cheese. And that makes a sandwich where there are 2 pieces of bread and 1 cheese. Well, I would expect it to look like A. If, however, I had, again, 2 pieces of bread and 2 pieces of cheese, and I produced 2 where there's 2 sandwiches where there's 1 piece of bread and 1 piece of cheese, well, then I would expect a sandwich that looks like this, but I'd expect 2 of them, right? So that's that difference between what a coefficient is, right? A coefficient tells us how many of this molecule we have, and a subscript, which tells us how many pieces of that thing are in our molecule. All right, we're going to be practicing this quite a bit. So please go ahead and click on to the next video to look at how we can actually start to balance by using our coefficients.